So here's another demonstration in the law of conservation of momentum. This one involves something known as Newton's Cradle. This is a really familiar device. You may have seen it before. A lot of people have smaller versions of this that they keep on their desktop just to distract them when they're getting bored at work. So these metal spheres collide nearly elastically. Every real collision is somewhat inelastic, but this is pretty close to elastic, meaning there's conservation of both momentum and kinetic energy when the balls collide. So let's try something. If I let one ball go, maybe I let it go from enough height that it reaches a speed of 10 meters per second when it strikes the others. So here's one possibility. The four remaining balls could travel away with a speed of 2.5 meters per second. 1 times 10 is just as great as 4 times 2.5. But that's not what happens. Anyone who's played with these before knows that one hits and one flies away. So the one that flies away must be going the same 10 meters per second as the one that originally collided. Okay. So maybe the rule is whenever things hit, only one flies away. So let's try this. If I release 2 from the same height, then when they hit, they should be going 10 meters per second. So if just one of them flies away, it would have to travel at 20 meters per second. A mass of 2 traveling at 10 is the same momentum as a mass of 1 traveling at 20. So let's see if that happens. No, it turns out the same amount of mass will always be in motion before the collision as there is after the collision. That's the only possible way that both momentum and kinetic energy will be conserved, because kinetic energy is proportional to velocity squared. If the speed and mass after the collision weren't the same, then because velocity is squared in the equation for kinetic energy, but only to the first power in the equation for momentum, there's only one way to conserve both. So that presents a bit of a dilemma. If I let 3 balls go, now there's only 2 balls remaining. So if these 3 balls are going 10 meters per second, okay, 3 times 10 would be 30, so these 2 balls would have to fly away with a speed of 15. But that's not what happens. If I let 3 of them go, then 3 of them go after the collision. Not only will momentum stay the same before and after the collision, it turns out in this case, the mass before and after the collision have to stay the same, so that the velocity before and after the collision is the same, so that both momentum and kinetic energy are conserved, which is the defining feature of the elastic collision. And there's some other fun ways you can do it. You can have them come from both sides, so release 2 and 1, and then it switches to 2 and 1 on the other side. Go buy yourself a Newton's Cradle and have fun experimenting with collisions.